Hello everyone. Today we'll talk about simulation. What is this about? Well, we have some random variable x, and everything we learned until now was different math models to describe the variability in x. So the way we described what's going on is using math equations. And that's really good. I mean, nothing wrong with that. But there's another way. And the other way is to obtain like 1,000 or a 10,000. Doesn't need to be that many, but with 1,000 observations from some random variable, then you can do a lot of calculations, a lot of probability procedures based on that list. So intuitively, the variability of the random variable x, when you have thousands of observations, you could plot a histogram and you see that it looks very similar. So the histogram and the line are closely resemble each other. Okay, so why would we go the simulation approach? So by the way, the simulation is the ability to create this sample of simulated observations from the variable x. So the reason, there are many reasons, but the main one is that it gets rid of all the math. Working with data, from chapter 1, you already know how to do calculation statistics on data sets. So you can leverage all your skills from chapter 1 to do probability calculations. Okay. Visualization is also useful. Rather than try to think about what the equation looks like, just plot a you can look at the data, either histogram or, again, all the things we learned in chapter 1, you can now apply them to study the random variable x via its simulated values. But the main reason why this section exists in the book, by the way, this is not often covered in other probability and stats books, but I really want you to know, is set up when we get to part 2 of the book. You learn all kinds of statistical procedures, and a lot of those, they come with guarantees. You say like, oh, trust me, this works 90% of the time. And normally statistics students, they have to take this answer on trust, on faith. You believe the teacher, the book is saying, giving you the correct formula. For you, if you know how to run simulations of random variables, you can actually test. Does the procedure really work 90% of the time? So by repeatedly applying it on different random samples, you can see what happens. Does it really, like, maybe you apply it 1,000 times? According to the guarantee, 900 of these 1,000 samples should produce the correct output. So this is very important for me because when I was learning this material, I kept checking to understand if things are really as I think they are. I ran a lot of simulations, and I think it will be useful for you too when learning to run simulations. Okay, so as usual, there's the notebook, section 27, simulations. I'll do a quick walkthrough of the book. These are things you're already familiar with. There's a new concept here. Okay, so given the data set, given n observations, data, we'll just call it data, there's something called the empirical probability mass function, converts the data into a probability mass function. And the integral of this function is the empirical cumulative distribution function. Okay, so that's really cool ideas that allow us to treat data as if they were probability distributions. So you see, you have to read the details, but it's really nice. Okay. Here are some applications, what you can do once you have the data from a random variable. And then we jump into a worked example. So the whole first part of the section is based on this random variable here. And actually, at this point, we're done with the random variable. We just generate 1,000 observations from it. So the e's correspond to a list of 1,000 observations from the random variable e. And then anything you might want to do with the random variable. So here is the graph. You say, oh, what does the distribution look like? Well, just plot a histogram of the e's. And then we add the line to check, is it really like, what is the true distribution is the line? And you see that it's actually pretty close, okay? Bunch of other things. So what is the mean of the data? The average in the data is 5.11. The true average is 5. Same for the variance, same for the standard deviation. So as you can see, you can obtain the statistics of the random variable from the samples. A bunch of other examples, anything you might want to do, even expectations with the random variable e, you can do it with the samples. Okay, then we talk about the definitions, this empirical distribution. Here is the graph. So this is the data, and the probability mass function you see here has all the weights where the data is. So it's an adapter from the data world to the probability world. And then of course, if there's a probability mass function, then there's a cumulative distribution function as well. It jumps for each data point, the empirical cumulative distribution jumps by 1. Well, there were 2 3s, so it jumps by 2 here. Okay. So then there's another section. So there's a bunch of material in this section. I would classify it as optional, but when we generated the data, right? So this is a random variable object from SciPy stats. And when we called RVS, so random variates, it produced n observations for us. So how does this work? Maybe you don't want to know, then you can skip the rest of the section, but I think it's pretty cool. So we were looking how exactly, what happens inside this call. Not literally, we're going to reproduce it from scratch because we don't want to read the SciPy code, it's too complicated. We start with the math, and this is how we're going to, this is a function that works just like a random variable generation from scratch. And you see that, so the new data we created looks kind of like the expected distribution. Here we compare the true cumulative distribution to the, do I have this graph? Yeah, here's a little bit better figure. Okay, and then we start with the big question is how, so we generated this new list EEEs2 using our own function. And then a very common question in statistics and in probability in general is like, does this data that we generated come from this distribution. So the histogram and the cumulative distribution plots were good visual checks, but in the book we discuss a bunch of other more sophisticated plots for the quantile plot, which you have to read. We compare the quantiles in the data and the quantiles in the distribution. This is where it works. It should look like all the points should be close to the diagonal. So it seems to be okay. And when it doesn't work, like this is exponential data, comparing it to a normal model, you see there is discrepancies. It's not on the diagonal. And similarly, from the student's t versus the normal, the tails don't match. Okay. And there's another way called the Kolmogorov-Smirnov distance, which is to plot a little bit like we did here, right? Compare the cumulative, the CDF of the true distribution and the CDF of the data, and then say what is the maximum distance. So this happens, if you zoom in here, it happens right here. If you look at it, this maximum distance is this much. So it's in a way it's saying like this is how much they're off. The worst discrepancy happens is this much. Okay, so to conclude, and why this section exists is because of this table. Let me make it larger, and hopefully Google will choose this as the screenshot. If not, I'm gonna make this the screenshot. All right, so everything is math, right? So the probability theory is mathematics. And the tools, we have functions that describe the probability distribution, and using integration we can obtain the cumulative distribution function. Okay, very good stuff. Now the practical or the data world, so is an equivalent way to compute. Instead of having a random variable x, we have observations from it. Again, think n is in the thousands or 10,000, like a lot of observations. Not like if you have a sample like 10 observations, you can't you cannot use the techniques in this chapter. You don't have enough data. So I'm careful not to use the word sample in this section. I'm talking about like a lot of data, like simulated manually or through other means. 10,000 observations, thousands of. Okay, so the equivalent, the probability distribution in the data world is called the empirical distribution, which you have to learn about. And then the equivalent of the CDF is the empirical CDF. Okay, and then the cool part is, okay, so let's say you want to compute the mean of the random variable. Well, you compute the mean of the observations. You want to compute the variance of the random variable? Compute the variance of the data, and so on and so forth. Expectation of some function x, h of x, same thing. Probabilities, just count the number of observations that, for the event, count the number of observations that are between the bounds of the event. So this side requires you to know math and deal with complicated functions. And in statistics world, this will still exist and it will still be complicated. This stuff requires knowing how a Python for loop works. No matter how complicated things get in statistics, in part 2 of the book, this will always be an option. And in fact, we'll keep coming back to produce simulations to test that the math works. Okay, so hopefully this section makes sense to you, and just one more to go. All right, have a good day. Bye.